Hi everyone, my name is Moshe Cosicher and welcome to What's the Scope? This is a student initiative hosted by Eastern Engineering Group where students get to pick out a structure and we contact a design team to see if they are willing to give us an interview where they will answer all of our design and technical questions. If you don't have time to watch the videos, we also have a podcast channel. You can look us up on Spotify and also Apple Podcasts. It's going to be under What's the Scope or under Eastern Engineering Group, so you should definitely go follow. Today, we are going to be speaking about Panorama Tower, the tallest building in Miami. We are very excited. This is going to be a very cool interview, so you should definitely check it out. Moshe, how are you?
Hello.
Okay, I'm still driving.
You're still driving? That's totally fine. This is Ryan and this is Shannon, and I know Danilo accepted the invitation a couple of minutes ago, so I think we're just waiting for him.
Okay. I'll be driving towards Panorama, and I'll be parking, I guess, in the parking space down below.
Oh my God, that's so cool.
No, we can talk from there.
That's gonna be interesting. All right, perfect. So Danilo's here also. Hi, Danilo.
Hi. Can you hear me?
We can hear
Yes,
you
we can hear you perfectly.
And you hear me well. Okay, that's good.
Can you hear us?
Yeah, I see. Bene. Okay, so this
Hey,
one,
Danilo, ¿qué pasa?
I guess. I invited Moshe too. No, man, I'm leaving.
Actually, I'm driving, so I'm very mobile at this moment.
Driving, okay. All right.
It's called Panorama on Wheels.
Listen,
Oh my God,
Moshe.
so funny. Well, Danilo and Moshe, welcome. Thank you so much for taking the time out of your day to just meeting with us. We are very excited to talk about Panorama Tower. My name is Monique, and this is Ryan, and this is Shannon. I'm just going to say that we're going to talk about Panorama Tower today. We are very excited because it's the tallest tower in Florida. It stands 868 feet tall, which is crazy. And we're just very excited to speak with you and for you guys to answer our questions. Shannon and Ryan, do you guys want to give a little introduction of yourself?
Yes, hi.
Good afternoon, Mr. Nani and Mr. Cosicher. It is very nice to meet you both. I thank you and appreciate you both for taking the time to meet with us and expand on what we know so far about the Panorama Tower. My name is Ryan Ocampo, and I am a first-year graduate student pursuing my master's degree in structural engineering at Florida International University here in Miami. I am actively involved in several organizations pertaining to the field, including American Society of Civil Engineers, Structural Engineering Institute, and much more. Yeah. I'm excited to learn more about the Panorama Tower as its height and its design have transformed the Miami skyline to what we know and see today. Thank you.
No, appreciate it
very much.
What brought you to structural engineering? A lost bet? You lost a bet and you were making up.
Yes, that's why. No, so I love structural engineering since I was young. Like I always admired the buildings in downtown and Brickell and how the city of Miami has been growing. So like I've always wanted to like play a part in Miami's growth, like help out in designing structures and like have more visitors from like different countries come to Miami and like play a part in that.
Okay, that's nice. And Moshe, pay attention because I see that you're driving for real. I want to lose that.
Right now I'm stopped, but the car is moving again. Okay, go ahead.
Aye. And no, that's nice. I mean, the interest is commendable. for engineering. Actually, you are in an area where there is a lot of high rises. Even in this pandemic, we're getting more and more projects that we're going vertical, and for the good or for the bad, we keep on designing and eventually building this kind of structure. And Shannon, you're also in the mix.
Yes, my name is Shannon Stever, and I am a civil engineering student at Florida International University. I am working on my bachelor's and master's through FIU's combined degree program. And I'm also involved in American Society of Civil Engineers, as well as Engineers Without Borders and Water Environment Federation student chapters. And I'm excited to be here, and I want to say thank you for taking the time to meet with us and answer our questions about the Panorama Tower. And I'm very excited to learn more and hear your guys' input.
Listen, you want to grill the architect first with the architectural question.
Yeah, en pensamiento, in thinking that I started the project 3 years before you got involved, and I had to have a very wide view. Oh, by the way, here's Panorama. See it?
Yeah, no, Moshe, try to end up in one piece. Right?
All right, I want to park in a spot where we can see Panorama, unless I get rained out. Actually, no, I'm going to get rained out. I better go and find cover. Okay, so 3 years before Danilo got involved, as you know, architects getting into programming the project, getting to finalize the marketing, governmental agencies, restrictions, FAA, which was one of the questions that you all posed. And I had to somewhat of a preview before I could sit down and draw anything. So this is how architects do their work, which is they go ahead and they make a list of all the forces that affect design. Engineers do that as well, but after we have somewhat of a conceptual envelope of what we intend to have in terms of bulk, you know, size, height. So what happens is that we go ahead and make a list of all the things that are going to affect our design. And based on those restrictions, we have a real project. You know, architects normally they don't draw pretty pictures. We intend to draw a pretty picture after we have a real set of conditions, which is, you know, all these things that affect the final design of this envelope. So what are the things, basically, some of the questions you ask? You know, we have a building that is not in Morocco with all the filigree. It's a building that is in Miami. It's influenced by our social economic culture of the city. We don't try to impose, or at least I don't, something that doesn't belong in the vernacular. And Panorama is a real project. It's something that responds to our culture, to our Latin American and quasi-European people that live here. After all, when we do a building that is multi-use like Panorama and has a population of about 1,800 people, you know, we want to be able to satisfy their wills and wants in terms of, you know, socially and their work and play condition. In Panorama, since it's multi-use, people can stay here and really not even go out. They can work here like I do. I work across the way at 1101. What I was getting at is that we're going to have, we have 1,800 people. We have 821 apartments. We have about, I don't know, somewhere in the neighborhood of 250, 300,000 square feet of office and retail between the annex of 1101, which is part of the entire complex. And here's where people work and live. I am one candidate that works and lives here.
Okay.
You know, to go ahead and design that people live comfortably under this mega block is somewhat of an accomplishment, because the future of our cities will be somewhat designed under this this concept where it's self-sufficient and we avoid traveling from one city to another or long distances. The use of the automobile will be somewhat curtailed. So, you know, this is something that it's somewhat accomplished with the Panorama project. Okay. Any other thoughts that you have that you want me to answer?
I think what we're gonna do
Oh,
is
here we go.
maybe Ryan, go ahead and maybe start asking the questions the way you want to do it, and then if we have anything left for Moshe, which I think we do, we can just go ahead. But you can just start with the questions.
Yeah,
I mean, I can tell you how it was conceptualized and how it started, but basically, in that regard, it's kind of a complex, because buildings that are privately owned, they must match a certain budgetary restraint. When you do a building that is institution or is government owned, I mean, you have a certain budget, but there's more freedom, because when you do a private project such as Panorama, 1101, and this complex, it has to make money. We live in a capitalized society, and this project, they put in well over $600-700 million so it can provide a good profit, and that's the way it is in America.
yeah.
Okay.
It takes away the poetry.
Right, and if an architect or a structural engineer, for that matter, and Danilo and I had many discussions back and forth about, you know, reevaluating, re-engineering, value engineering some of the elements of Panorama, is because it had to come in within a certain budgetary means.
Yeah, yeah, indeed. And what I can try to do, maybe, let me see if it works. I have a presentation that I used previously on Panorama, so it has some graphic that we can connect the words to. Let me see. Let me see if I can share the screen. Just and tell me if you see. Boom, boom, boom. Okay.
Excuse me, while you do that, Danilo, I'm going to sign off for a moment. I'm going to park my car.
Yeah,
and,
no, I don't.
And then I'm going to come back to you once I reach the lobby, okay?
Yeah, I don't want to use the architect and the friend. I know that we are getting there. Please.
Yeah, I don't need to see the video. I know Panorama. Go ahead.
All right. All right. So basically, in the meantime that Moshe parks the car and we avoid losing Moshe. So you see this, you see the screen?
Yes, we see it.
Okay, let me try something.
I'll see you in a bit.
Okay, I'll see you.
Okay, let's do this. You see now the screen?
Yes.
Okay, perfect. So that's what we're talking about. This is Panorama, and this is you know, the 860 foot that you were mentioning, the 83 story, the 90 story podium, and this is the tallest tallest tower that is mixed used. You know, basically it's as Moshe was saying, there is basically the opportunity to do a little bit of basic things, like you have retail, you have office, you have a gym, you have several amenities, and then you live there. Now, what you see here is all symmetric because this is a presentation that was given for the CTBUH Continental Building actually in Shenzhen in China, which was focused on the foundation of Panorama, which is part of your question. So the what happened with Panorama, and we can restart when Moshe logs in. So that's okay. There's a little presentation of the company. Now you were asking about the foundation. Foundation was done basically in collaboration with a company that's called MV5, the former Keiko, which is doing a lot of buildings from the geotechnical point of view, and this is part of interesting because it reconnects to your question. Now, to do this kind of high rises, part of the problem is what we have in our soil. Now, as you know, all these high rises, they are on Auger cast pile. You need to grab a competent soil, which you can find it going like 100, 120, 130 foot under the surface. And that's what we did with Panorama. Panorama is rest on Auger cast piles. And what we are doing with all these Auger cast pile, this is the location of Panorama that is here highlighted. Obviously, for you it's not a problem. You know where Miami is. You know the proximity to the water. So this basically is what we consider that you have this limestone. So one of the first steps when you design a building is to understand what is the soil condition. And that's what we did. So you get a geotechnical report. The geotechnical report is based on investigation, and those investigations, they give you the local rocks that you will rest on. So this is basically the concept and pictures of what you will see under the surface of Panorama. And at a certain point, you use Auger cast pile, which is the most economical and the best way to reach the depth that you need to reach. Now, what is the limits of Auger cast pile? The limit of Auger cast pile is that those are no wider than 30 to 42 inches. They go to a depth of 150 to 160 feet. And that is where every tower that you see around, like we have Miami World Center, we have Lateral, we have the Aston Martin is going up, 1000 Museum. They all have piles that goes to this depth. This is what substrate profile look like. This is the one for Panorama. So what you're seeing is that you have sand when you have close to the surface, and not very competent line rock going a little bit under the surface. Then again, sand that is sometimes it's a problem because you have piles that tends to be shorter, the one that support building up to, let's say, 14, 15 story. So you may get into the problem of having piles that have a lot of sediment. And then you go basically into more competent soil when you go deeper. And you keep going down until you have the required capacity for the pile, which happens to be on the depth. Now, one thing that is important to consider is when you have the displacement of the pile. When the pile gets loaded, it has a displacement. The displacement of the pile, obviously, the displacement of the building. Based on that, you estimate a settlement of the entire tower. In this case, the settlement was estimated 3-4 inches. Like often happens, this building at the old Panorama settled 6 inches, so more it was expected, but it was designed to be resilient, so we anticipated basically the fact that it could settle more. So, what is Panorama peculiar? I know that there was a question about the frequencies. The frequencies of this building, basically, I don't know if you see the mouse. You see the mouse? So there is, you have basically a component of wind that goes in this direction, component of wind that goes in perpendicular direction, and a tendency of the building to have torsion. Now, this building was stabilized to be fairly rigid for the height. The period is 5.7 seconds, and the other direction is 5 seconds. So the building is stiff in the both direction, and torsional is the third mode, which is the stiffest, which is the one that requires the most energy to be able to get, to a degree that it can basically move the building, which is about 4.2 seconds. What does it mean to me? What does it mean to have a building decoupled? It means that when the wind, let's say, goes in this direction, like Collie X argument saying, it doesn't force the building to torque, which means that a lot of structural elements can be designed with less reinforcement because it doesn't induce a torque. It only induces a displacement. So it's basically when you resonate, when you play piano, when you resonate a violin, and you see a certain point, a certain notes, the glass start vibrating. You're basically capturing natural frequencies of that material. Now, when we have the wind, and the period of the wind is in seconds, it tends to have basically the wind naturally acting on a frequency that is forcing the building to move regularly back and forth, naturally so, or straight in this way, without adding a torque component. So that is critical. How you're doing that? You're doing basically by placing the shear walls in a symmetrical way, and being more specific when you have the center of wind, which is basically you have, let's say, wind that in this way, you will have the center of rigidity more or less where the center of wind is. And this happens on the other hand. Then the other idea is you try to have a certain floor, what we call belt trusses, which are basically enclosed walls that give stiffness and prevent the building to really open apart. These are the forces in shear, which are 15,500 kips and 7,500, which are massive. Then this is what it looks like an analysis when you basically have the what we call the belt trusses, and this is the two belt trusses. You have basically, this is ETAPS model, which is this is one of the questions, what kind of software we used, that's the ETAPS. That is the interstory drift. Now, when a building is this size, it's controlled by interstory. What is the interstory drift? Basically, is the displacement that you have between two floors. This displacement is typically L or H, which is the slab to slab, divided by 360. So that is the controlling condition, rather than being the strength of the elements, which means in a building this tall, the problem is mostly to keep within the limit of serviceability, not that much that some elements are basically overstressed, which means that if it works that for deflections, chances are that that wall can also take the stress. Now, this is the modes. This is the other question, 5.8, 5 and 4.4, which is the modus of the couple. One is basically is dominating the X direction, Y direction, and torsional. The acceleration at the top is 7 milli-G on 10 years, which is within the limit of easy occupancy, in the sense that in an hurricane, you shouldn't feel the acceleration. Now, the limit is about 10 milli-G, 50 milli-G, depends if it's an office building or a residential building, which have different tolerances. Now, the thing here is that these milli-G are not torsional, so the movement occur in this way, so they're less perceived. Now, we have the architect back here. Here we got into foundation. Moshe, do you want to say some words on the building, on the picture, before I show some foundation? I see you're back and safe.
Oh, I think, yeah, your microphone.
Hello.
Yeah.
Danilo, what is it that you want me to review?
I mean, you have basically the building that has a certain shape, certain prominence, and in a podium. I think what I would like to know is how the big elements go together. Like, for instance,
Okay.
why the podium is like this.
I can give you an idea how the puzzle began. We had a parking structure that previously we had a parking structure and the two buildings of 1101 sitting on a piece of property that is about, let's say 400 feet, for argument's sake, 400 feet irregular by 400 feet, okay? Which is approximately close to 4 acres of land on Brickell, to which half of it was occupied by the two buildings, the two office buildings that face Brickell, okay? There was a third structure, which was the parking structure of 9 floors that occupied the east side of the property facing Brickell Bay Drive. Okay, that remaining piece of property, once the parking structure was demolished, it had a certain shape. And the shape on that 2 acres allowed me to restore the parking that I had removed and add the additional parking that I had to do or provide for the Panorama Tower. So I had to put back the 700 some odd cars that I had removed temporarily, placed on another piece of property that Mr. Hollow owned, and provide new. So what basically you have a podium that was, say, 250 feet by 250 feet, or pedestal, as you may want to call it, that housed the entry lobby, loading, mechanicals, on 13 floors, and of course, 2,000 parking spaces, together with about 100,000 square feet of recreational areas to be provided for the Panorama users, and a pool deck, which is another 50,000 square feet of a deck on top of the podium. In addition to that, that podium also houses 206 room hotel, which is our Hyatt Centric, which is part of the project.
Correct. Yes.
So what there remain is a podium and a tower. Now, someone, I don't know who is it that addressed that this is a slender building. This is not a slender building. This is a typical wide, the typical width of a residential tower, which is about 80 feet wide, okay? It's 80 feet by 240 feet long, somewhere in that neighborhood. And that is, the length is based on the design that architects will give it. Sometimes they do it, if it's longer, they make it on 2 towers. Maybe they do a split tower. You know, there's so many different configurations that a design can take at the tower element. The pedestal, the podium, had a shape towards Brickell Bay Drive, which is somewhat curvilinear, which basically is not something I invented. It follows the shape of the road, and the shape of the road has that curve. So I went ahead and used it towards the design, and that's why you have that odd or curvilinear shape at the podium, facing the front of the building, which is Brickell Bay Drive, and then the tower sits behind it, which gives you a very nice shape. I was going to park in front on that little corner, which is my favorite, and show you, but I didn't want to get rained out. So, I mean, you can log in and Google Earth it and see how interesting those shapes take effect on the corner of Panorama. But all in all, you know, we architects are responsible in making sure the building works with our consultants, with the engineers, with the mechanicals. I mean, this is a massive project. This is like, imagine one cruise ship turned up. You know, it's almost 900 feet high, and it houses, you know, 821 apartments, which is a population of about 1,700 people, plus all the other ancillary facilities that become part of it. So this is like an ongoing day-to-day ship that needs to work with all of the environmentals that have an effect on it. Go ahead.
I have a question. Mr. Cosicher. So how do you and Mr. Nani like coordinate with the podium, since there was a curvilinear shape, and like did the surrounding buildings like pose any challenges like into designing the building?
This is like horse and jockey, okay? We ride at the same time. There is nothing that Danilo would do or I would do without coordinating with each other. The fact is that and he will explain to you, the fact is that we have a point load, let's call it, okay, and I'm not using the right structural terms, but the tower is like a point load on this podium. And the building's stresses get displaced at the parking levels. Now, in the old days, you would have to put beams to take that weight and displace it towards the side, like a buttress. But the way this building has been designed by DeSimone, it allowed me to be basically beam free at the parking level, so I could have my driveways be operative and functional without having a drop beam that will carry the load. So this is by the use, and Danilo will have to explain to you, by the use of the slab working together as a diaphragm with the huge shear walls that we have that go from end to end. They were able to accommodate the thrust of this tower that is about 60 stories high or 600 feet high, that becomes a point load on the center, somewhat in the center of this podium.
Yeah. So you want to tell this kid the real story, that you were taking out the columns and I was putting back the columns.
Right.
I
mean, listen.
Okay.
That's what we architects do. We try to fight with the engineer. Says, no, I cannot have this column in the middle of the room. You got to move it over. And Danilo was very creative in, we have columns here that are slanted. You can't see it, but they're hidden inside, and they're slanted 20, 25 feet from one point to the other at the parking garage. So
that's actually one way to solve. That's very good said, Moshe. Columns can slope, and that's what we did. We sloped 2 columns. So this is a typical floor. If you have the typical floor just brought straight down into the parking, obviously it conflicts with everything. So what Moshe was saying, when you have walls like this, you have to somehow to drive through. So this one is one example of what we need to do. So basically you have the core, but here you will have an opening. So that's the opening that you see. And so it's a little bit complicated, because what you need to do, you need to have this area reinforced with huge steel plates. Now, the other thing that Moshe was alluding to is that even the regular columns that needs to be transferred. We have something like 11 transfers in this building, 2 slope column, and 6 of these, or 3 couples of this element, outrigger element. So that's what creates the complexity. So the building looks very, let's say, with a straight line outside, but a lot is happening inside. So, and let me see if I can tell you something a little bit. There was a question about the foundation. So you have like 36-inch diameter piles, and you have a pile cap that is a typical 12 feet thick, and we use grade 100. So with Moshe, we've been using materials that typically not used. The code today is not clear about the grade 100. It's limited to grade 80. So in order to go to grade 100, and we had a discussion with the city and with the peer reviewer, which is a company that reviews our drawings, and we basically had a performance-based design, meaning that we proved with records of the test of this steel that much tension was achievable. Now, some numbers, 447 piles, and this is basically the discussion. Now, on the settlement, this is what it looks like when you have the big hole, and you're working on filling the hole with the piles, and it's huge. It's huge because it's a lot of concrete, a lot of water that may go into that hole. So there is all preparation, and also there is a little bit of need to basically retain the soil with sheet piles. Now, things keeps going, and this is what's happening. You know, you start building what will be the area where you have the elevators. This is the analysis that you see next to it. You see most of the main pile cap is connected, not to have differential settlement. And then when you go into the real deal, this is about 13,000 cubic yard. It's huge, 600 workers. And it's basically something that takes, is continuous. Now, everybody, a lot of projects in Miami claim to have the longest continuous pour, but this is within 28 hours. It's been huge. And so I would say so far it's not been surpassed. Now, if we want to be a little bit cool in engineering, we did for this project, just to make sure that Moshe doesn't have to suffer the problems that comes with settlement, sensitivity analysis on piles. So what happens if the piles are a little bit stiffer or less stiff? Than what happens? That what the geotechnical report will give you. So in a building of this caliber, there is a tendency of softening of the foundation exactly in the center, under the let's say under the core. So what you have in the geotechnical report to be 1,300 kips inch, so it takes 1,300 kips to lower 1 inch. In reality, could be less than that. Could be only 1,100 kips. What it means that when you run the calculation, it may be more deformation under the core, which it doesn't change what happens on the pile. The pile tends to receive, because they are designed by equilibrium, they statically, that the same basically load, but is the deformation is different. Therefore, it imposes a load in the pile cap, which can bring to substantially different forces, and it translates in a need for additional reinforcement, which means that if you just do the calculation for a pile cap without considering this kind of effect of softening, which happens with the time, you may end up to be short with reinforcement. So you will have to have an area that you can call a compression zone, an area you call a tension zone, that basically will give you a need to have additional reinforcement. So you will have to envelope the result that you get with piles. They are a little bit stiffer and a little bit, softer than you originally designed. That could bring to additional reinforcement needed that could prevent the cracking in the pile cap. Now, a pile cap of that nature typically doesn't fail for a moment or tension. It fails in shear. But it is not a good thing to initiate a cracking of a pile cap, even because of moment, because it reduces the resources available for shear. It's cracked concrete. So, and beside all the problematic you can have if it cracks on an elevator, and you can have, water intrusion and whatever, or additional or more settlement that due to basically a not perfect functioning of a pile cap. Now,
so Mr. Nani,
Nimelo.
So based on the pile cap softening and the shear force cracking, do you guys have to change the pile caps? Like which pile caps you ended up using?
Man, the pile cap, it still was the same layout, the same piles. Is the top and bottom reinforcement that were enveloped. So you basically you consider the range of value that the stiffness of the pile can basically be, depending on permanent transient loads, which means wind. So what you typically find out is that if the pile is towards the center of the building, is softer than you think it is. If it's at the edge, it's behaving harder. So it takes basically more load, to attend the center deformation, which means that you end up to have more bottom reinforcement at the center of the pile cap and more top reinforcement. Let me see if I can go here. Here, in tension zones, you will end up having more top reinforcement. And here, since this thing, instead of deflecting like this, it deflects more, you need to add more bottom reinforcement. So that is interesting, let's say, something that you only see in building of a certain, I would say, we'll call it caliber, but they can generate this kind of forces, they can generate this kind of compression zone and test the piles in this way. So these piles, with the time, they get loaded more than what we're supposed to be. For instance, here around the real core, even though there is so much structure, you can really see at least a 5, 6, 7% in the load just because of the geometry. Even though not by calculation. By calculation is correct, but you have to add this effect of displacement that tends to load more the center. So just to give you an idea how complicated it may get. This is what you see here is settlement.
È toccato.
Eh? Che passò?
No, I'm talking to Benji to see if the air conditioning closet here fits. That's all. Never mind.
Che apprende.
I'm working.
Insegnagli che apprende.
Sì, che apprende.
Che apprende. Sì, now, this is how you monitor a building. You have a settlement point. So what you're doing, you locate basically area, you determine area with you have like sensors. They give you the settlement through the life of construction and the life of the building sometimes, and you see how the building settle. Why is that important? Because it's not the case of this building, but a building can tilt, like we have in Sunny House. A typical example is Aqualina, which is basically this tilting he went down 13 inches and tilting as well. So tilting happens when one area is softer, and you basically building tends to start tilting that way. So this is another thing. When the building is not symmetrical, you try to have the piles to compensate for it and have the same amount of load or putting more piles if where the building is heavier, less pile when the building is lighter, so that in average the building goes down straight. And that's what happened to Panorama. So by monitoring this, you start seeing that the inches, that the total settlement approaching 6 inches. The building was supposed to settle like 3 inches, it settled twice. It is not unusual. The settlement starts when you are about a third of the tower, because it comes with some connections between the hourglass pile and the soil get broken. So you start some settlement, and then the settlement basically is a combination between elastic compression of the pile and the displacement that he has basically, due to the load and the movement that you have in the soil. So this,
Mr. Nani.
yes.
So how, like, what would be the reason as to why there's like a large difference in settlement between 0.5 and 0.7? Because based on like the figure, they're really close to each other.
Yeah, but for 5.7, the difference is the load, because 0.5 is the area where you are basically collecting a lot of load, and more it is the softening effect. 0.7 is an area that you expect from the beginning to basically settle less. Now, what is less? Typically, the buildings are designed to be able to absorb 1 inch differential settlement every 30 feet. So if you have, let's say, at the center a settlement of 6, you should expect at 7 something that it could be 4, 3 in that neighborhood. And that's what you can easily, let's say, justify and work with in terms of differential settlement. Now, differential settlement is due because of difference in the loads, is due because of the behavior of the soil that tends to create like a ball. So that's why the center of the building tends to settle more for these two reasons. Now, the a building like this, with these walls that they protrude, tends to somehow to mitigate this effect, because once you have a stiff wall, that wall cannot bend. So there are some rotation, there are some movement still, but everything is kind of very much connected. But I can tell you that if you wouldn't have this connection here, certainly this settlement would have been more significant. Also, there is something else about the settlement. Let's take a 0.5 and 0.7. 0.5 and 0.7 goes through an important connection of the building, which happens to be here. Now, if we look at the way that this building works, we go to the scheme of the analysis. You see my mouse? Yeah. Can you see something moving?
Yes.
Okay. Now, if you see, let's say that you have a settlement here, which is the 0.7. This is somewhere at 0.5. If the differential settlement is too much, they create basically a differential movement that affects this girder. By doing so, it induces a force that is not due to the wind, because this is designed for wind. So if you have wind on this wall, hitting a tributary portion of this wall, and you have the point of rotation here, this thing wants to rotate, and this needs to be compensated. You can either bring it here, consider it that is balanced by a force here, Let's say you want to rotate a cron around this point. So you can already figure out what kind of work is done by this connection. Now, and this already gets a steel plate. Steel plate, they are like 30 foot or 35 foot long by 10, about 10 foot high. And there is, it could be a couple of plates. They are each 1.5 inches. So you have 3 inches or more of solid steel taking that. Once you do that, if in top of this you have this piece of the building that move this way and wants to shear off, then you have adding some serious forces into this connection. Therefore, it's so important that here there is a foundation connected to mitigate this shear off. So these are all consideration, I guess, a little bit more sophisticated. It comes with experience with having building other building and looking what's happened to the other engineers, how they get in trouble, how to stay out of trouble. But once you have an element, a connection within the building that is already working very hard and is taking, so much shear that the concrete cannot take it anymore. You just have to do with solid steel. You want to do everything you can to avoid putting additional shear by settlement. Therefore, you try to connect as much as possible. And also to place the pile in a way that they minimize the differential settlement. There will always be a difference, but you try to minimize that. And the difference is explained from the fact that you will have never enough permanent load here compared to what you have here, regardless how many piles you put here and how less pile you put here, So there are certain characteristics of the building, because what you see this here, this edge is this edge, comes down from the tower, but this edge, it comes
Danilo?
Is Monique, is you?
Yeah. We lost you for a second, so I was trying to make sure you weren't there. Yeah.
Okay. When did you lose me? You lose me 1 hour ago, half an hour ago, 10 minutes ago, 5 minutes ago. When did you lose me?
Probably 10 seconds ago.
10 seconds ago. Okay, no problem.
Yeah.
Okay. So basically, what I want to tell you is that the key of making one of the key of making a building so complex to work is that it doesn't change with the time the original structural configuration. And one way to get in trouble is excessive settlement or differential settlement. As long as the building goes down all in one piece, it's fine. If the building tends to shear off some of the elements, then it can create cracks. And if the cracks are in the wrong location, like in an outrigger that supports the building, people start to get excited. And that's, that's what we try to avoid.
Okay.
So that's, it's a resilient building. It's a stiff building, a resilient building. It's supposed to perform good with all kind of solicitation, which is hurricane. So he already proved himself with extra settlement. So I can reassure Moshe that this building is gonna stay vertical for a while. Actually, the owner, the Tiborolo, one day asked me to wanted to be reassured that I understood that he wanted to have the tallest building and not the longest building, So the building was to stay vertical, which so far this was supposed to happen. So I think we we give like a first pass, at least to give you like an idea of what is involved in doing a tall building. Now, right now with this mess of this coronavirus, we are limited. But what we've been doing, Moshe and I, what I've been doing on the engineering side, we're giving a presentation. There is an organization called Council on Tall Buildings, which I'm co-chair for Florida. This presentation actually went to China within the same organization, which is a worldwide organization. And what we're doing, we're analyzing a tall structure from all point of view, from the developer point of view, or architect, structural engineer, with the intent to share the knowledge. We have been doing presentation here in Miami before this pandemic. We will restart. I prefer to do like a live presentation with some wine, prosecco, things, that is like, more interactive, more fun. But this one is, the next best thing. But in general, we will restart when there is something, I hope that soon we will be able to sit, with, distancing, but, sit down somewhere. So, I don't know. I mean, if you take a look, if you have any question or anything that jumps to mind. Let me see.
I don't know, Ryan, do you think there was something we didn't cover? I don't know if Shannon maybe wants to ask one of her questions. I know we have maybe like a couple that are a little bit more personal.
I do have a question for Moshe.
Moshe disappeared. Moshe.
Okay, so I can revert the question to Mr. Nani.
Yes.
What computer software was utilized in the design of the Panorama Tower?
Panorama Tower. This is mostly ETABS for the lateral system, for the superstructure. When you do the walls, basically, when you do the slabs, use RAM concept. When you do foundation, use SAFE. These are basically the three programs that you want to master. In this case, I would say the most important is ETABS, because once you have the forces, once you have the behavior of the building, in a tall building, I would say ETABS is the one that you have to really know the best. And I would say the other two, the same, same importance. They are just doing a different. They have different purposes. So.
Was there like a sequence of like when to design like the slabs, the foundations, and let's say the whole structure? Like you design the foundations first, and then design on ETABS, and then like do you design the slabs on RAM based off the analysis on ETABS, or were they analyzed separately?
Yeah, they're separate, because we tried not to have the slabs separate from the lateral system. So you typically, what you do, you set up the walls and the alignment of the columns. Then you will have that working with ETABS. You get revised loads from the wind tunnel, which reduce what is basically needs to be designed for from the requirement of the code. You typically can reduce up to 20% the wind forces. And then once you bring the loads down to the foundation is where you use SAFE. Now, there are elements, they are a little bit particular, like the bell trusses. Bell trusses are like a closed wall. They could be 1 or 2 level high, that serves to basically eliminate the torsion within the building. Those bell trusses are also designed with ETABS. And there is the pool deck. Pool deck is typically designed with safe because it's not post-tension. Kind of never has post-tension because of all the reverse of load, like the pool may or not have water. So there is something that needs to be designed conventionally. And otherwise, this is bringing down the load into the foundation. And the sequence of doing a building like this tall, the battle is always to stabilize for wind. The rest is kind of following up. So it's the first step. And then you obviously have the two characteristics of determining the total cost. So a building like this have several interactions with the ownership and contractor to try to minimize the cost of the structure. That is also kind of another stage. And then basically, and off you go. You try to get a good contractor so that, you know, you can sleep at night, they know what they're doing, and you start building it. Yeah, that's basically. So that's the idea.
Did like the stiffness or like the components of the building like change like the final price of all the structure?
Yeah, I mean, here is the thing. If you need to have a certain stiffness. The stiffness you can avoid with the quality of the material or with the size of the walls, the geometry. A building like this that doesn't have a very stringent restriction of the size of the walls, you basically use a local material and keep the stiffness by mass. Other building, you cannot have the geometry to have the walls as thick as you would like to have, so you need to fill it up with steel, and it makes it more expensive. So basically, the consideration here for this building was to have the right geometry in the walls, because we didn't have to worry too much about the sizes of the wall compared to other projects, but we had to worry about the total amount of reinforcement because it was starting to be huge, and what is expensive is the reinforcement more than the concrete. So that's the consideration in this building was mostly to minimize the reinforcement within the wall. So when you design a column, you try to stay with 1%, or even less in certain cases. When you design a wall, you try to have not 1% more, but not to be very heavily reinforced, because really what makes the cost more and more tends to be the reinforcement. So yeah, that I will say. Bene, bene. So now I would say I will keep Monique. Let's keep in touch for you know, send me the contact when we start with the CTBUH. You know, that would be a way to go to reconnect. I will soon disappear from the radar because today I need to try to go to Italy, to UK. So it's at a certain point we'll have to go to the airport and try my luck because it's there's still a lot of restriction.
No, of course, be safe. Thank you so much really for showing us all this information. It was actually very insightful. I know we learned a lot by everything you showed us today. Please be safe on your trip. Take all the safety measures. And
I mean, it doesn't depend on me. It's the plane. It depends on the plane. It depends on the plane and the pilot.
I know, right?
It doesn't depend on me. If it were for me, that nothing would ever happen. But it doesn't depend on me. These are the two things. But yeah, in the whatever is possible, I'll do. So, ladies and gentlemen, I'll start getting ready, and it was a pleasure. And I'll disappear, fix a couple of things, and I go to the airport.
All right. Pleasure meeting you.
Right.
It was a pleasure meeting you.
Bye.
Thank you. It was nice to meet you.
Bye.